All right, limit calculus, day number 1. We're going to talk about definition of limits. Let's do it. All right, so what are limits? Let's talk formal language and then we'll make this simple. For a in the real numbers, the limit as x approaches a of f of x exists if and only if both the limit as x approaches a from the left of f of x and the limit as x approaches a from the right of f of x exist and are both the same value. In this case, the limit as x approaches a of f of x is equal to the limit as x approaches a from the left, which is equal to the limit as x approaches a from the right. So the left-handed limit here, I'm going to draw in blue. The limit of that function from the left and the limit of that function from the right agree. They both exist and they agree. Therefore, we know that the limit as x approaches 1 of f of x, which is x plus 1, equals 2. One way you can do this is you can just evaluate, right? What would f of 1 equal? Well, if the function is x plus 1, then we could plug in this 1 and our limit comes out. Too simple, right? Well, there are other scenarios as well. Let's get to those. All right, so let's look at this first scenario here. Let's say that y equals x squared minus 1 over x minus 1, and it's not defined at x equals 1. Why? Because, well, if you did a direct substitution in this case, right, we want to evaluate the limit as x approaches 1 of x squared minus 1 over x minus 1. If I plugged in that 1 like I did on the previous problem, I would get 0 over 0, which tells me there's something else going on. Right? If you get 0 over 0, or as you'll see later, infinity over infinity, you get something funky. So what do? We factor the numerator. This is our first method if we get a value of 0 over 0. So if I factor the numerator, I'd get this, and leave the denominator as is. You'll get a cancellation, and you get x plus 1, right? So now the limit as x approaches 1, as you can see going on here, they do a direct substitution, they get 2 as well. So in order for the limit to exist, the output at that point actually doesn't have to exist. There could be a hole there, but the limit would still exist because the left hand and the right hand side agree. Now here's an example of a limit not existing. Right, so the limit as x approaches 1 of this function, y equals 1 over x minus 1, will not exist because the left-hand limit and the right-hand limit, they don't meet, they don't agree. So therefore, let's read this part. There is no finite real number that f of x approaches as x approaches 1. So the limit of f as x approaches 1 does not exist. So some syntax that you might see for does not exist. DNE, another example might be this backwards E with a line through it. Both of those mean does not exist. Does not exist. Okay? All right, let's keep moving. All right, so let's look at this example here. Consider f of x equals this piecewise function, right? And you can see that this piecewise portion is right here, and this piecewise portion, oops, I got those backwards. So that piecewise function is right here, and this piecewise function right here. So just looking at this graphically, this limit does not exist, right? Because as the graph comes from the left, it looks like it equals 2. As it comes from the right, our y value equals 1. So as x approaches from the left, f of x approaches 2. So the left-handed limit would be 2. As x approaches 1 from the right, f of x equals 1. So it looks like the left-handed or the right-hand limit equals 1. Therefore, since these two limits are not equal, there is no unique value. Therefore, this limit would not exist. Okay. We can make f of x as close as we'd like to the value of 5, right, by making x large enough. Okay, as x approaches infinity, now this is called an infinite limit. Okay, excuse me, limit at infinity, right? Because now x is approaching infinity. So now we're starting to get into this end behavior talk. So as x approaches infinity, what we'll notice is that our graph, our y value is approaching 5, but it's approaching 5 from the bottom, right? And our left-handed limit, or our limit at infinity going the opposite way, of f of x is approaching 5 from above, right? So if you look at that, it's approaching 5, but also from above. So this is a limit at infinity. Okay, take that note. This is called a limit at infinity. All right, we're going to talk about infinite limits another day, but this is a limit at infinity. Okay, so a few properties of limits. I'll kind of roll through these pretty quickly. If f of x equals a constant c, where c is in the real numbers, then the limit as x approaches a of f of x would equal c, right? Pretty plain and simple. Let's say that f of x equals 2, right? So here's f of x. Let's say x approaches 4. Well, the left-handed limit and the right-handed limit, well, their limit as x approaches 4 of f of x would have to equal 2, right? It's just a constant, that's all it is. Okay, some other properties. If we take a limit with a constant out in front, right, then whatever our limit is, this looks like a d, but it's actually c times limit. So let's say the limit as x approaches a of f of x is L. If we have a constant times f of x, we could pull that constant out and multiply it by the limit. So let's say the limit as x approaches some value a of f of x equals -7. If I wanted the limit as x approaches that same value a of 3 times f of x, we could say that would be -21. Pretty simple. Right, a couple others, sums, right? If I have two functions, I want the limit as x approaches a of those, I just take their limits individually and add them. Product here, quotient here, power rule here, and power rule in a different form there. Okay, so now we get to this idea of this limit at infinity, right? So say you've got this function, right, in red. U of n is the function. Okay, L is the limit, and epsilon is going to be this tolerance, so to speak. Subway sandwiches was an old example we used. I didn't really feel a good connection to it, so I'm not using it this time. But as n increases, right, as n goes off to infinity, what you're going to notice is that this gap, right, this epsilon right here, is going to be the tolerance, or how close our estimate, right, based on sigma, or delta, so to speak, how close is it to the actual limit? So as n goes to infinity, right, as n goes to infinity, the window starts to squeeze and get closer and closer and closer. That's what a limit is, right? So our left-hand limit and our right-hand limit, we wanted to meet, right? We want this upper end of epsilon right here and this lower end of epsilon here to squeeze and give us some limit as n goes to infinity. Let's go ahead and show on the next page how to use that. All right, so what we want to do to show that a limit of terms exists, we show that there's a relationship between n and epsilon, and then we show that as n increases, epsilon decreases, right? So that's just going to squeeze that window around the limit L. So here's how you do that. First thing you do is you take your function, 3n over 2n plus 1, absolute value of that minus your limit. And we want to show that it's less than epsilon. Okay, and what we want to do is we just want to show a relationship. So in order to show this relationship, what we do is we get a common denominator. So I'm going to multiply top and bottom here by 2. And I'm going to multiply top and bottom here by 2n plus 1. Okay, so let's go ahead and simplify. Okay, so I get this, 6n over 4n plus 2 minus 6n plus 3, and what you'll always see is the 6n and this n cancel. Alright, and what you'll get is negative 3 over 4n plus 2, common denominator, is less than epsilon. Okay, so at that point, I've shown that there is a relationship between n and epsilon. Okay, so step 1 would be complete. So step 2, what are we doing? We want to prove that the limit of u of n equals 3 halves by showing that as n increases, that epsilon decreases. Okay, so as n increases, epsilon decreases. So here's step 2. Step 2, we're going to take our function, actually our relationship, negative 3 over 4n plus 2. And what we're going to do is we're going to show that epsilon, which is what this equals, right? Well, we could say epsilon's less than that. But we're going to plug in 10. So let's plug in 10. So that'd be, and the absolute value of this would just make no difference. Right, so that'd be 4 times 10 plus 2. So epsilon is less than that, which gives me 3 over 42, which I believe comes out to 1/14. So epsilon would be less than 1/14. If I did the same thing again with 100, right, if I did that with 100, then that would be 3 over 402. And therefore, I've shown that as n goes to infinity or increases, epsilon decreases. Decreasings. Okay, cool. Now what did I do? Okay, I've proven that 3 halves is the limit of this function. Now you might remember back from the old HL1 days that if I took the limit as n goes to infinity of this thing, 3n over 2n plus 1, right? The degree on the top is 1, the degree on the bottom is 1, so what do? As n goes to infinity, our relationship is the coefficients of those highest degreed powers. Alright, so there we go. That's the formal definition of the limit. Let's get to some other stuff before we move on. Okay, first of all, let's do a couple of these exercises here. Sketch each function to determine the existence or otherwise of the limit of these functions. Okay, so if you ever have a linear function or a polynomial in general, there will never be any issue with asymptotes or anything like that. Now in this case, where I have a rational function, there might be an asymptote or there might be a hole. Alright, so here I'm not worried about this at all. So I know that the limit as x goes to, negative 1, right? As x goes to negative 1 of this, 3x plus 2, I'm just going to direct substitute right in there. And when I plug it in, I get plus 2. So it looks like I get negative 1. So the limit as x goes to negative 1 of 3x plus 2 is negative 1. Done. So if I were to graph that, right, it would look like this. Here's 2, da-da-da-da. When a equals negative 1, it looks like my value, my output is negative 1. So my left-hand limit and my right-hand limit, how can I just assume that? Well, because it's a line and it's continuous everywhere. No holes, no asymptotes. Okay, the next one, what I would probably do is I would do a direct substitution right away. So the limit as x approaches -2 of the following function, right, input that, over x plus 2. Well, I do a direct substitution, which would mean I'd have 4 minus 2 over -2 plus 2. There's some funny business going on because I get 0 over 0. Therefore, my first method would be factor and cancel. So on the top, I'm going to factor. And it looks like I'd get a +2, -1. I can go figure there's an x plus 2 in the denominator. So it looks like there's a hole at -2 conveniently. So the limit as x goes to -2 of this new function x minus 1, I believe direct substitution would give me -3. Okay, so let's go ahead and graph this for a minute. This is x minus 1 with a hole at -2. So x minus 1, there's -1 as its y-intercept, and a slope of 1 with a hole where x equals -2. Okay, and that hole is located at y equals -3. Therefore, the limit still exists. Right? Left and right still agree. However, there is a hole there, so you want to be careful. Okay, let's sketch one more here. Sketch this function, f of x equals sine x for greater than pi over 2. So let's remember sine x 2 pi, here's pi, get that out of the way, here's pi over 2. So sine x has a value of 1 at pi over 2. Okay, and then it comes down and does one of these fun things. There we go, this would be -1. Okay, 2x over pi when x is pi over 2 or less. So let's first evaluate this. Let's take 2x over pi, and let's just input pi over 2 there and see what would happen. So it looks to me like those 2's would cancel and the pi's would cancel and I'd get 1. So there's a hole there, and it's got a slope of 2 over pi. I'm not really going to sketch that at all. I don't know exactly what it would be, but that slope is 2 over pi. All right, so does it agree? Does the left-hand limit as x approaches pi over 2 from the left, and the right-hand limit as x approaches pi over 2 from the right, do they agree? Yes, they do. Therefore, the limit of f of x as x approaches pi over 2 would be 1. All right, let's look. Is there another one on this page? No, there isn't. Okay, this one's cool. Let's sketch a graph of this. This is going to be kind of crazy. Okay, so I'm assuming that this would be 3. Let's do this in blue, in green, in yellow. Okay, so x squared where x is greater than 3. So this would be a 9, not to scale clearly. Okay, so just bear with me here. It's not going to be perfect. Okay, x equals 5 when y equals 5 when x equals 3. Okay, so here's 5 when x equals 3. All right, and 3x if x is less than 3. Well, I would have a situation like that. Right? How do I know that these two are going to agree? Well, I know that f of 3 for this is 9. I know that f of 3 for this is also going to be 9. But then what do I do here? Like, there's a gap. Doesn't matter. So just because there's a discontinuity and a hole in the graph doesn't play into the fact that the left-hand limit and the right-hand limit agree. Okay, so if I evaluate the left and the right-hand limit, right, my left-hand limit right here as it approaches 3 from the left is 9. My right-hand limit as it approaches from the right is also 9. Therefore, does it exist? Yes. And yes for part C because the limit as x approaches 3 from the left of f of x is equal to the limit as x approaches 3 from the right for f of x. Check. We're on it. One more. All right. I just want to cover this one right here. Does this limit exist? Let's sketch it and see. What does the square root of x look like? It looks like this. Okay. Does this limit exist? Well, there's a problem here. The right-hand limit is 0. So the limit as x approaches 0 from the right of f of x is equal to 0. But there's no limit from the left. Limit as x approaches 0 from the left of f of x. It doesn't exist. Therefore, since these two limits don't agree, that limit does not exist. Okay, it does not exist, or backwards e with a line through it. All right, guys. I think that's probably it. No, you know what? I'm going to do this last one here. F. I want to evaluate this limit, and it does exist. First thing you want to do is direct substitution. So let's substitute in. That'd be 1 over 5 minus 5 times 1 over 5 minus 1 over 5. We got a problem here, right? This would be 1 over 0 times 0, or 0 over 0. So we got an issue. So my method on this one, we don't have a whole lot we can do with factoring. Therefore, what I'm going to do, I'm going to leave the outside alone. And on the inside, I'm going to get a common denominator. Okay? Let's do this. So let's take 1 over y, and let's multiply top and bottom times 5. Okay, and then let's take 1 over 5, and let's multiply top and bottom by y. How about that? So what does that do for us? Well, limit as y goes to 5 of 1 over y minus 5 times, we get 5 minus y over 5y. Oops, I don't know why I put a 5 there again. It'd be 5 minus y over 5y. Okay, so let me compress this a tiny bit. I'm going to squeeze these both into 1. So this would be 5 minus y over 5y times y minus 5. I just multiplied. These two right here are really, really close. Really, really close to the same. So let's do a quick adaptation. You might notice that if you took a negative 1 out of the top one, it would change that to be equal to the bottom. Therefore, these two would cancel. That means there's a hole in this graph at y equals 5. Therefore, we can now do a direct substitution. Negative 1 over 5y. If I do a direct substitution, that would be negative 1 over 5 times our inputted 5. And it looks like we're going to get negative 1 over 25. So that limit, as y approaches 5, would be negative 1/25. Okay, I think that's good for today. That would be day number 1 on the formal definition of the limit and limit existence. Peace.